So our last talk of today is from Professor Poul Nielsen. So Paul is the go guy when you have a problem and you don't know how to solve it here in ABI. So have a lot of background in different parts of what we do. So he is working on instrumentation, computational models, quantitative methods to better understand biological systems. And in terms of his biography, so he works in many projects that is coupling mathematical modeling with novel instrumentation techniques that allows to understand and interpret measurements of complex biological systems, subject to the construction of well-understood physics, conservation, and balance laws. So thank you very much, Paul, for accepting this talk, and I'm keen to hear what you have to say about Subvox.
Okay, thanks a lot, Gonzalo. Actually, I was going to begin this talk with an apology because my research is neither AI-driven nor really focused on medical imaging. So what am I doing here? Most of the work that I've done over the past few decades has really been focused on aspects of soft tissue mechanics and energetics, and combining both the experimentation, the development of instrumentation, and interpretation of measurements using model-based approaches. And really that has been driven because the tissues or the problems that we're dealing with are, we're wanting to get a better understanding of living systems, right? So when you have living systems, as soon as you start to, tease them apart, cutting tissues out, for instance, you are damaging the system. The tissues typically die, and you lose their integrity and all of the mechanisms that contribute to their underlying mechanics and energetics. So some of the work that I've done in with PhD students and my collaborators in soft tissue mechanics has focused on mechanics of skin, for instance. I'm involved in the the breast research unit, trying to get better understanding of breast mechanics to allow us to track tumors within the breast under different loading conditions, under different imaging modalities. I've also spent a fair bit of time working with modeling childbirth, quite difficult modeling problems that really are dependent upon a good understanding of the behavior of the tissues involved. But what I'm going to do here is talk a little bit about an algorithm that we developed half a dozen years ago and have been refining since then. And it was developed out of a necessity, because in order to get a good understanding of the mechanics of living tissue, you need to be able to perform experiments in vivo, or at least it is very, very helpful to do so. So one of the sort of threads of research that we've had over the past few years is trying to get a better understanding of the mechanics of skin in vivo. And one way you can approach this problem is, as I said before, not cut tissue out, but do the experiments on individuals. How can you do that? Well, you can apply well-known or measurable forces and torques, to the surface of the skin. That's readily available, and look at the deformation of the skin under those measured loads. Now, that induces generally a quite a complicated strain field, and hence, depending on the properties of the tissue, stress field. So how do you go about getting some useful information about that? Well, One approach is to have your experiment to gather the data under the known or measured loads. You can see or record the movement of the tissue using video or photography. But what you really need to be able to tie those two together, because that doesn't give you any information, direct information about the mechanical properties of the tissue under study. What you need is some sort of realistic physics-based model in order to interpret the information that you are gathering from your experiments. So typically in a situation like this, we would apply the loads, we would measure the surface deformation of the skin, and we would set up a corresponding finite element model where there are things about that model that we don't really have much information about. In particular, the parameters that describe the constitutive behavior of the tissue. But what we can do with that model now is adjust the constitutive parameters until that model coincides, with the measurements that we make on that system. And that turns out to be a very powerful way of enabling us to make good estimates to identify the mechanical behavior of the tissues in vivo in this case. So it was that problem that really drove us to thinking about, well, how can we accurately track tissue? Because the thing is, it's not a particularly well-posed problem to adjust the parameters of your constitutive model in order to sort of match up with the deformations you observe experimentally. So in order to improve the accuracy and the robustness of that approach, we really needed to be able to track the deformation fields as accurately and robustly as we could. And that was the motivation for us developing Subvox, which I will describe here. So essentially, Subvox is a particular algorithm or set of algorithms that allow us to accurately register pairs of images. What do we mean by registering? Well, there are many ways in which you can register images, and Matthew, was giving a very nice talk just previously about sort of global methods that he's been working on. How do we match up the features in these different images, or they could be 1D, 2D, 3D, 4D even. How do we match them up? Well, there are different approaches here. Many techniques involve identification of particular features and try to minimize the difference between the unregistered and registered positions of those features. Others are purely intensity based. They don't require the identification of features. They're just looking at the local texture of the two images and trying to match those up. There are image registration techniques that operate on whole images, and that's great for homogeneous deformations. Others are looking more locally, trying to find the displacement, the relative displacement at a large number of points. They typically operate on registering sub-images. There are registration approaches that are rigid. They either translation and rotation. And others are non-rigid. And again, Matthew was talking about the non-rigid approaches that he was using. Some deal with single modality. That is, the two images are acquired using the same technology. and yet others are multimodal. So if you're, for instance, trying to register MR with CT, then that would be an example of multimodal registration. And of course, there is the dimensionality differences as well. Okay, with that in mind, how do we quantitatively measure the correspondence? You know, whether two parts of an image are well registered. And again, there are a variety of techniques that can be used. Sum of squared differences is essentially a measure of the dissimilarity of two images. We can use, so in that case, you're trying to minimize the dissimilarity. Alternative approaches involve cross-correlation, normalized cross-correlation, and that's a measure of the similarity of two images. So in this case, you're trying to maximize the cross-correlation in order to register the images. And then finally down here, mutual information is yet a more complicated way of registering images. And it's very similar to the cross-correlation in the sense that it is trying to give you a quantitative measure of the similarity, but the nice thing about mutual information is it works well across modalities. In our case, we were focusing on images of the same modality. So cross-correlation or normalized cross-correlation, you know, was the obvious choice for us to quantify the similarity. We also had at our disposal the earlier algorithms that essentially quantified the rigid displacement of two sub-images in order to get a localized deformation estimate. Cross-correlation was used as the measure of goodness of fit, partly because it behaves you know, very nicely under images of the same modality. Just as a sort of a background here, cross-correlation will give you the relative displacement of two sub-images identified as a peak in the cross-correlation of those two images. Essentially, you take one image, reverse it and slide it across, as we've got down here, slide it across at different lags, and when the two images or the two signals are most similar, you will get a peak in the cross-correlation. So it's often, you know, quite well defined the point at which you are reaching the maximum similarity between those two sub-images. It also performs reasonably well under noisy conditions, or at least when one of the signals is noisy and the other one isn't. When you get both signals noisy, well, the cross-correlation signal is, although it will have you know, a reasonably well-defined peak, that is often noisy, which makes it quite difficult to find a good estimate of the relative lag between the two noisy signals. Okay. Okay. Often the cross-correlation is a very computationally expensive task to perform. So generally, especially for large, you know, sub windows, it is far more practical, computationally tractable to not perform the cross-correlation directly, but to do that in the Fourier domain. because cross correlations in the spatial domain are equivalent to pointwise multiplications of the signals in the Fourier domain and then brought back into the spatial domain. So it does require a Fourier transform of the signals of interest, but the calculation, that pointwise multiplication, is very, very cheap, and the the forward and inverse Fourier transforms are relatively cheap. So overall, it is useful to use the Fourier transform in order to speed up your cross correlation calculations. But of course, a Fourier transform assumes that you have a periodic signal, and of course that causes issues at the boundaries of the sub-windows that you are looking at, because in general, the signal at one boundary doesn't match up with the signal at the other boundary, and you can get aliasing effect, or rather ringing effects, because of that mismatch. Essentially, it forces some high frequency components that get in the way of performing the cross correlation accurately. So typically what is done is to window your signals, or window your sub images. And there are many different windows that you can employ. They all have their sort of particular attributes, positives and negatives. Very simple windows like the triangular window, the Fourier transform of that is relatively narrow, but you get relatively high frequency effects still occurring. Most widely used are perhaps the Gaussian window, Hamming-Hahn and Blackman window, which are trading off these sort of effects of ringing with the sharpness of the ability to find that peak. Okay, with that in mind, how do cross-correlation based image registration algorithms work? This is a basic traditional cross-correlation registration where we've got our two images and we have located two sub-images that are roughly in the same region. They have similar features that we are trying to match up. So those two sub-images are identified, they're taken out, they are windowed with an appropriate window function. They are normalized so that we can accommodate changes in illumination intensity, for instance. Fourier transform is taken of both of those. One of them has a complex conjugate, and then we pointwise multiply them together. So we end up with the Fourier transform of the cross-correlation function down here, and then we take the inverse Fourier transform and we will end up with our cross-correlation function that hopefully has a peak at the corresponding to the relative displacement of these two sub-windows here. That's okay. It's, as I mentioned before, not performing particularly well on noisy images, because it's very hard in your cross-correlation function to find the maximum to within a few pixels. If you have a very low noise sub-windows that you're cross-correlating, then it performs reasonably well. In that case, you can typically get the relative displacement of those two sub-windows to, within something like 1/5 of a pixel, all right? That's fine, but we think, or we realized about 20 years ago, that you can do a lot better, especially because we are taking this approach here of performing the cross correlation in the Fourier domain. We've already got access to the Fourier transform of the cross correlation. And we'll come back to that in a sec. So, what happens now if we've got some choices to make here? As I mentioned before, if we have inhomogeneous deformations, then we are, by using this algorithm, the traditional, cross-correlation based approach, we are only able to find the relative displacement. It doesn't pick up any rotations, and it doesn't pick up any inhomogeneities of the displacement over the image. So typically what you have to do is look at sub-images that are relatively small, and to then try and match up those sub-images. Those sub-images give you a sense of locality. The support is relatively small, so that the information in those sub-images is going to be constrained to the relative displacement within a small region. That's somewhat tedious, because typically you're wanting to, if you want good locality, then you need to have small sub-images. On the other hand, and you need to perform that in a large number of points across your image. That's one problem. The other problem is that it's a lot easier and more robust if you can compare two images that overlap considerably, right? So as soon as, for instance, you are able to, or you have images that are, say, more than half the window size apart, then you've only got a relatively small region of overlap, and your cross-correlation measure then becomes somewhat dubious, because you've only got such a small region that you can make the comparisons. So one approach is to say, well, okay, we've got this trade-off that we're going to make, or have to make, between the support of the sub-image and our ability to locate the position or the effect of the relative translation, and our sort of locality and the ability to do the comparison robustly. So one approach that we've taken is to take a hierarchical approach. So start off with relatively large sub-images so that you've got a good deal of information to compare against. That gives you a very robust measure then of the relative displacements at the larger scale, but it doesn't give you very good locality. So what you can do is use that information in a hierarchical sense, looking at successively smaller and smaller sub-windows, each time applying the relative displacement that you've discovered or identified from the larger sub-windows, thus getting a relatively robust and yet ultimately localized set of estimates of deformation. All right. So this is the approach that we have applied to, measuring the regional displacement of skin. But look, we've got some more information in this approach. As I mentioned before, the cross-correlation has been performed in the Fourier domain for computational reasons. But there is information that we can take advantage of in the Fourier domain using the Fourier shift theorem. If we have two images in the time domain or the space domain, and one is shifted relative to the other, then the cross correlation is going to be, have a magnitude, a magnitude that is invariant, that is the same as the signal in the time domain. But the Fourier transform of the cross correlation is going to have a phase added to the signal, which is proportional to the shift. If we have no shift, then we will have no phase shift in the Fourier domain. If we now increase the relative shift between the two signals, that induces a phase shift which is proportional to frequency in the Fourier transform of the cross correlation. The nice thing about that is it's a lot more robust to measure the gradient of that phase versus frequency in the frequency domain than it is to try and identify a single maximum point in the cross correlation in the spatial domain. It is not only more robust, but it is also far, far more accurate method to estimate your shifts. You are now looking at information over all of the frequencies in the frequency domain from the Fourier transform, as opposed to trying to identify a small number of values in the cross correlation in the spatial domain. So it's that trick here that provides you with orders of magnitude better estimates of the relative displacement of your subwindows. Okay, and it's relatively straightforward to calculate the the gradient of the phase with respect to frequency of the Fourier transform of the cross correlation, except that phase wraps. This phase is bounded between plus and minus pi. As soon as you have a shift more than 1 pixel or more than 1 unit, then at the higher frequencies, you will get phase wrapping occurring. And that's a real problem, because trying to unwrap or trying to interpret a phase wrapped signal is quite difficult. So how can we avoid this? Well, one approach that we have taken is to take a two-step approach. In essence, we use the traditional approach of the traditional Fourier transform-based cross-correlation identification of the maximum of the cross-correlation in the spatial domain to get within 1 pixel of shift. And then, having got that, we use the phase-based approach in order to estimate the subpixel shift, right? In this case here, we can be guaranteed, if we are within plus or minus 1 pixel of the true shift, that we will avoid any phase wrapping occurring. So in this case here, that two-step approach gives us the robustness as well, the robustness of the traditional approach and the accuracy of the phase-based approach. So this is essentially the idea that went into the an algorithm that we published back in 2002. So in this case here, just the part of the algorithm that is dealing with the subpixel shift. So here we've got our two images as before. Here we've got our two sub-images that are the same part of those two images. But what we do is shift our sub-image an integral number of pixels, which is determined by the unit-based approach, the traditional approach where we've identified the peak of the cross-correlation. So that step there allows us to shift our sub-image, the second sub-image here, by an integral number of pixels or units. And we go through the same sort of approach here, windowing, normalization, Fourier transform, and performing the pointwise multiplication till we end up here with the Fourier transform of the cross correlation. Now we can use the Fourier shift theorem to measure via least squares or some sort of fitting process the gradient of that Fourier transform of the cross correlation, and get from that a very much more accurate estimate of the relative shift of these two sub-images based on the integral number of pixel shift and the subunit pixel shift. This approach here works very well, but it has been improved even further it can be improved even further by taking a more judicious choice of windowing function, especially you're not constrained to using the same windowing function for the unit shift algorithm and the subunit shift algorithm. Not only that, you can greatly improve the robustness of the unit shift algorithm by filtering the signal or the image. In particular, if you apply the sub-image, apply a differentiating filter to the sub-image, and in fact, we've tested something called a Savitsky-Golay differentiator, which has the effect of deprecating or lowering the influence of low spatial frequency components of our sub-windows and emphasizing the higher frequency components up to a certain point, and then for very high frequency components, again attenuating those. In that case, that provides a very much more robust way of conditioning your images in order to get a better estimate of the unit shift. It is not only more accurate because it emphasizes the components of the sub-windows that are best giving you the best estimate of the unit shift, but it is also a slightly low pass filtering in a sense. It's actually a sort of a mid pass filtering. We call it filter being applied. Using this approach here, we're able to get subunit shifts accurate to within 1/100th of a pixel. Of course, that depends on the quality of the signal that you've got but using off-the-shelf cameras, monochrome cameras, we've demonstrated that the subunit shift algorithm using this approach here is typically accurate to about 8 millipixels. So we've tested the algorithms, this combined, unit shift and subunit shift algorithm on Landsat images. There are there's a whole sort of traditional test suite. These are not medical images, of course, but they cover a wide spectrum of, different image types. And it's actually, relatively widely used, these Landsat images, to test the relative performance of the registration algorithms. Using that approach, we tested a large number of published algorithms and against our one here. So this work was largely done by Amir Haji Rasulullah about 5 years ago. For relatively small, i.e. subpixel shifts, you can see here there's sort of a random set of subpixel shifts. We could get a relative performance which was considerably better than any other published algorithm. Okay? So the closest that came to the accuracy for small shifts of our algorithm was Stone et al., which is another phase-based approach, but many of the others are considerably worse, as you can see. Not only that, but we tested it on large relative shifts. So these are, you can see, all greater than 1 pixel shifts. So this is more a measure of the robustness, because algorithms that fail to pick up the integral number of shifts, relative shifts accurately, really completely fail. And in this case here, you can see that there is, again, a considerable difference in the performance of these other published algorithms compared to ours. Okay, so here is a sort of a practical demonstration of the performance of the algorithm. Essentially, we've got a speckle target which has been placed on a rotation stage, and the rotation stage has induced a very small angle of movement in that target. And you can see that, well, that's down to 40 millipixels. So the consistency of the estimation of the displacement around this region here is, yes, in the order of about 10 millipixels. And practically, you can see, the slight change in the pixel intensities that correspond or that are induced by the very, very small changes in position of the target. This is closer to the original intention of the development of the algorithm. This is Amir's hand, anonymized hand. He should have a something covering it, but you can see here the relative displacement in this video image from the first image is consistent, and although it doesn't really have high resolution down, to the subpixel level, there is certainly good deal of consistency in the estimates of the measurement. So this is more of a demonstration for large displacements beyond 5 pixels, for instance, than the accuracy demonstration of the previous video. We've applied the algorithm to quite a number of different imaging modalities and different problems. In this case here, this is a 2D slice, MR slice through two individuals, where we're measuring the deformation of the brain in that mid-sagittal slice as a result of the ballistic flow of blood to the brain. So in this case here, this is a healthy individual, and you can see that there are deformations in the order of 0.2 of a voxel, or pixel in this case, because it's only 2D, compared to a Chiari individual where the cerebellum is being pushed down into the spinal region, and the ballistic blood is loss of momentum with each heartbeat is inducing relatively large displacements. So it's an indication that such techniques, because of their sensitivity and their accuracy, may be able to assist with the identification and diagnosis of particular pathologies. This is still relatively early days for this work. And this is just a 3D. As I mentioned earlier, the algorithm works in an arbitrary number of dimensions. Computationally, it becomes a bit more difficult to perform the 3D registrations, but it's still relatively efficient compared to any other registration algorithm available. So, in summary, Subvox, in our tests at least, it's the most accurate published image registration algorithm available. It's not only accurate, but it is also very robust in the presence of noise and robust in the presence of large deformations. It is computationally cheap. It's not really much different in computational cost, to any of the other most efficient registration algorithms available. It provides direct control over locality versus accuracy by enabling the user to choose the sub-image size. Clearly, as you reduce the sub-image size, you increase the locality of the information or the estimates of deformation, but you're also reducing the amount of information that is available for the registration process. So the estimate of the registration for smaller sub-windows becomes less robust and less accurate. But you've got that control completely in your hands. Returns quantitative information about the relative displacement of sub-image pairs. So you're getting back your estimates of the relative shift of those sub-images in terms of the underlying pixel or voxel size. You can use hierarchical sub-imaging to effectively remove the relative motion between image regions. So again, it's that locality, ability to control the locality that is quite useful. It's been used in multidimensional data. We've tried it on 1D, 2D, and 3D data sets across many modalities. We've tried it on camera images, MR, CT, ultrasound, OCT, and had relatively good results from all of those. And finally, you can use or apply the algorithm in sequences of images where you are either traditionally have had to compare all of subsequent images with a reference image. But of course, if you have large deformations, eventually that registration will fail because there's just not enough overlap between the two images, or they are not similar enough. Or you can compare, pairs of images throughout the time course. But of course, there you're getting relative displacements from one image to the next one, and then another relative displacement from the next image to the next one, right? And of course, if you want to get the total deformation, then you get an accumulation of errors. But we've applied a technique based on the image registration algorithm that we've developed that looks not only at the relative displacement of pairs, immediate pairs of images, but also immediate pairs but one, immediate pairs but two, and so on and so forth. And that provides you with a good deal more information that increases the robustness of your total deformation estimate, but it also decreases the error associated, the total error associated, because you're effectively averaging the noise over many separate comparisons. So that's been applied to measuring the movement of the gut over time. We do have a website that allows you to try out Subvox, at least for 2D images. So it's pretty forgiving about what sort of images you supply. But on the website here, if you upload a couple of images, it will attempt to give you the relative displacement under some control of yours, with regard to window size, etc. That, I guess will allow you to see whether the algorithm performs well or not on the sorts of images that you're dealing with. So all of this work here, of course, has been done by our team over a number of years. The original work was done as a master's project by Dwayne Malcolm, and then it was improved considerably by Amir Haji Razulaha for his PhD. And more recently, a lot of work has been done on this by Robin Lavin, who's back here. And with that, questions.
Greg?
I presume it doesn't work very well when you've got scaling or large rotations. What's the cutoff for each of those that it can cope with reasonably?
It is a pure translational measure, but it does cope relatively well with rotations. Of course, how large a rotation depends on the information content in the images. But in the original paper, 2017 paper, we did some tests on how well each of the published algorithms, including ours, cope with rotation, and it performed relatively well. So scaling, yep, that's certainly an issue. With scaling, you're sort of essentially focusing the region of possible match, close to the center of your sub-image. So that will degrade the estimate of the the cross correlation as the result.
I presume those could be kind of pre-steps in the same way that the large deformation step you could.
Yeah, so I mean, I think the algorithms, all of the, rigid registration algorithms, could be improved by including, scaling factors and rotation factors. But in essence, that would be sort of a non-linear or iterative search, just a repeated application of the base algorithm. But we're thinking about, how we can apply affine transformations to sort of maximize the cross correlation.
Yeah, well, a scaling one is sort of like sub-image size, so that you have a different sub-image size within each of the two images that you're registering. So
well, it's not really, because in scaling, you have a parameter that is essentially a real number associated with the relative magnitude of the. Excuse me.
Once you go to an affine transformation or a scaling, you will start being in an interesting situation where the coefficients of your discrete Fourier transform don't necessarily line up anymore. It's easy to think about the scaling, because obviously if you scale by 1.5, all of your discrete offset functions, so that's very comparison. The approach you have to take to the solution is not much more. Essentially, rather than being sort of a linear fit, it has to take into account the offsets.
Well, I have a question regarding the robustness towards noise.
Yep.
So I saw that you put Saltpeppers and Gaussian, but what about if you have noise like similar to the ones that you have in ultrasound, multiplicative, Rayleigh noise, gamma distributed noise?
Yeah, we haven't quantified that. We've certainly tried to register ultrasound images that we've acquired. And at least qualitatively, they seem to be robust. But no, we haven't quantified that.
And is there any way in the method that you can include a model of noise if you have it? Or the best approach will be to try to remove the noise and then process it?
I'm not sure that it is sensible to try and remove the noise, but if you know the characteristics of the spectral characteristics of the noise, you can certainly use that information to pre-filter, the sub-images, so that you emphasize the parts of the spectrum that you have most confidence in.
Okay, yeah, makes sense. Like assigning weights to
Yes.
certain bias.
Yeah. So the algorithm, through the windows applied to both the spatial and the frequency domain, allow you to easily sort of replicate a wide range of filters. In essence, that's what we've done with the application of the Savitsky-Golay filter. We know that there is a sort of a range of spatial frequencies that is most robust, or provides the most robust estimates of relative shift, at least in the the integer pixel sort of range. So, and I'm pretty sure that's why the Savitsky-Golay differentiating filter performs so well in this application.
Okay.
And I'm sure again that's dependent upon the the spectral characteristics of both the sub-image and the noise characteristics.
Yeah.
Can this be applied to stereo vision cameras? displacement field?
Yes. Yep. Robin's the person to ask that question of, because you know that he has investigated that. I mean, that's most useful where you have, you know, relatively shallow angles of acute angles of view. As soon as you start to move the cameras, you know, to more obtuse angles, then the sort of matching of the information becomes much more difficult. But there may be ways, you know, that we can accommodate that, you know, through appropriate transformations of one image relative to the other.